So still trying to match the large pipe, 2,000 meter long, 12 meter diameter pipe. We have decided to go with a 10 meter long pipe that has a diameter of 6 centimeters, and that gives us geometrical similarity. And we have to go on with a smooth walled material because that's also required for geometric similarity. But we have to now match the Reynolds number, and the Reynolds number is going to allow us to have dynamic similarity. And the Reynolds number for the first pipe, the one we're trying to simulate, is 2.8 times 10 to the sixth. So in order to do that, we have to, of course, have RE based on D2 equal to RE D based on 1. So we're going to have U2 times D2 divided by nu2 is equal to 2.8 times 10 to the sixth. So that's straightforward. Now we know D2. So D2 is fixed by the geometries we've decided, and D2 is, of course, much, much smaller than diameter 1. So if this is much smaller than diameter 1, we have a couple of options for matching the Reynolds number. We can try to increase the velocity a lot. The diameter went down by a lot, big factor. So this velocity would have to go up by a big factor. Of course, there's some impracticalities with raising velocity forever. We could end up with, basically supersonic flow. That would be a problem because it would be no longer incompressible. And there would be a whole other set of parameters we'd have to try to match. So, we can certainly increase the velocity. It was 3.5 meters per second. We could go higher than that, but we might not want to just increase it tremendously. And then the second thing we can play with is the kinematic viscosity. So we could change the fluid. So we're going to do both. What fluids are available to us? Well, in what direction do these need to go? Well, obviously the velocity needs to get bigger. We would like the kinematic viscosity to get smaller because that will generate a larger number here. We have a smaller d, so we need a smaller kinematic viscosity to try to get closer to this Reynolds number. Well, one fluid, of course, that's often available and has a smaller kinematic viscosity than air is water. So that's readily available. So let's try using water. So let's try using water. And so if we use water, we'd have U2 times 0.06 meters, because that's the diameter of our pipe, our new pipe. We don't know the velocity yet. But nu2 is then going to be, equal to the 1 times 10 to the minus 6 meters squared per second for water. So we'll say nu here, 2, equal 1 times 10 to the minus 6 meters squared per second. All right, so that's my new idea. Because this is much smaller than 1.5 times 10 to the fifth, that's going to cause an increase in my Reynolds number. So now I'm going to just solve that for U2, right? So I'm going to set this equal to 2.8 times 10 to the sixth, because that's the Reynolds number I'm trying to match. I'm going to solve for that U2. And when I do that, I find that U2 is equal to 46.7. 46.7 meters per second. Now, that is really fast, but it is possible. It is certainly nowhere near the speed of sound. The speed of sound in water is actually 1,500 meters per second, so we're not remotely close to that. And water is truly pretty much just incompressible anyway, so we're not at any real risk of having compressible flow here. It's simply a practical issue of having water moving that fast in the system. That's a lot of pressure that's going to take to drive that flow. You have water shooting out the end at a very, very high velocity. But it's all possible. So we're just going to say, okay, we can do it like this. As I say, experimentally, maybe that's not really practical to drive that much water through a small pipe at that speed, but we could try it. If we wanted to try to get this down, we could try to come up with a different fluid. So we could try to have a fluid that had an even smaller kinematic viscosity. An example of a smaller kinematic viscosity fluid is actually just warmer water. So if for instance, at T equals 60 degrees Celsius, the kinematic viscosity of water is 4.75 times 10 to the minus 7th meters squared per second. So it's basically half, a little less than half of what it is at 20 degrees. So we could use this, and that would allow us to decrease our velocity by a half. So that's one option open to us. There aren't a lot of other fluids that have lower kinematic viscosities than water that are easy to access or use. So that's, there's a limit to how small we can get this and still use fluids that you really would have experimental access to. But anyway, we're going to assume that we just use water, and we're going to go ahead and keep this velocity the way it is and assume we can achieve that for our imaginary experiment that we're going to run here. So the next time we do it, we'll actually run the experiment and get a result.